Today my topic of presentation is Credit-2 scheduler. I have with me George, who basically designed this solution. So I only recently started working on it. I implemented rate limit patch and did this comparison task. So if any algorithm related question or design related, George will be able to help me. So I will get my presentation started. Based on my analysis, the documents that I read and my discussions with Citrix, Credit-2 scheduler was designed with the following goals in mind. First one is functionally complete with respect to Credit-1. And I think with the recent patches from Dario implementing soft affinity and yield, we are functionally equivalent to Credit-1. So there are four major functionalities, if I remember correctly: soft affinity, hard affinity, rate limit, and yield. All these are there now in Credit-2. Second was algorithmic improvement. George did some initial test, and Dario also tested. And they found that for real-time operations, Credit-1 algorithm was not suitable. The way it attaches weights, the way it attaches credit, and the way the algorithm behind how it distributes vCPU, how it moves pCPUs between different sockets, that was not giving appropriate performance. They did some initial testing, and there was a requirement for improvement. And so that was another reason why we came up with Credit-2. Scalable. Scalable, maintainable. Its code is much more organized as compared to Credit-1. New functionalities can be easily added, now to Credit-2. I tested up to scalable. I tested up to 64 vCPUs. I went to that level, and yeah, it performed well. And the last criteria was improved performance. As I mentioned about real-time requirements that were there. Apart from that, we aimed to improve performance, whether it's network throughput, storage, bootstrap, login vSite. So that was another aim while we designing Credit-2. So my topic of discussion will be improved performance. I will be focusing only on performance. Right. So I will be concentrating on 4 areas of performance measurement. One is bootstrap. We have this automated test where in bootstrap we will launch 25 VMs parallelly in different threads, and then we will note the performance, how each VM starts at what time. Then we have login VSI test, where initially it will be a bootstrap type, where the VMs are started in a batch of 25. After all the VMs have started, then we will run login VSI workloads, and the data collected by login VSI will be presented here. Third one is network performance, network throughput, and the fourth one is storage performance. So I think these 4 test suites should cover all the aspects of a scheduler with respect to the performance. So it will be all the slides are graphs. So I will be going a bit slowly, explaining each one. So this is total duration from invoking the first VM till the nth VM finishes logging in. So initially, it starts from, the graph may not be that clear. It starts from 0th location, and we are trying to launch 126 VMs. It's a 4-socket, 64-core, 64 logical processor system. And we are trying to start 126 VMs with 1 gig of RAM each. It's Win7 64 guest. And yellow is Credit-1, and blue is Credit-2. So the time it stops here, it's around 400 some unit. And the lower number is better. The earlier it finishes, it's better. So from here, it looks like the blue line is finishing first, and then the yellow line comes. So the blue line, that's the Credit-2, is better than Credit-1. But if you look at this dot, this VM starts at this point, and it's finishing later than all the VMs has finished here. And this yellow line and this blue line, they are equivalent on scale. So it's not that blue line, which represents Credit-2, is better than Credit-1. It's equivalent. There's not much to choose here. Total cumulative time is same for both of them because of this VM. It finished after all the VMs have finished for Credit-1 and Credit-2. Now, just to give a better picture, this is the mean of the longest gap between consecutive invocation of VM start. Again, the same test that was done earlier, but just another representation for Credit-1, it's 41, and for Credit-2, it's 44. It's milliseconds. Now, this is the duration of the nth VM cloned. It's again a bootstrap, but this is the total duration of nth VM cloned. Again, not much to choose. It's going simultaneously. Yellow one is Credit-2, blue one is Credit-1, and going almost same. Four socket, 64 core system, and here we are trying to clone 400 VMs. And this is the total time taken. It's around 400, or how many seconds? Yeah, around 1600, 1700, 1700, 1600 seconds, something of that sort. So yeah, and this is the VM index. It goes from here to here. Again, almost comparable, equivalent results. Not much of a difference between Credit-1 and Credit-2. This is just a, if same test again, 400 VMs I'm trying to clone. Blue one is Credit-1, yellow one is Credit-2. This is just to represent in a different form time taken by each individual VM to start. So the graph represents each individual VM, and the line here, it's the mean. And again, the yellow and blue mostly coincide. It's around 2 seconds or 3 seconds. That's the time, average time taken for each VM to clone.
How many iterations after test?
Sorry?
How many iterations?
Each time, I have performed around 2 to 3 iterations of each test.
So this is sort of a histogram with one particular test?
One particular test, yeah. The iterations are performed just to make the results are consistent. Now this is the login VSI workload. Here, this one represents Credit-2 and this one is Credit-1, and of course lower is better. As I mentioned earlier, in login VSI, first we complete bootstrapping, and then after all the VMs have booted, then we start the login VSI workload. And in login VSI workload, we run various applications, and each application logs a point when it completes. So at the bottom, it's the system is 4 socket, 60 cores, 120 logical processor hosts, and we are trying to start 600 VM with 1 vCPU each. And yellow one is Credit-1, blue one is Credit-2. Lower number is better. So here, lower number is better, Credit-2 looks better. And there's not much gap to start with, but as we increase the number of active section count increase, there is an increase in gap, and then there is a decrease. I think, yeah, it's a bit narrowing down. Now, this narrowing down doesn't mean that Credit one is picking up on speed or it's performing better. I had a discussion with performance team, and they told me that as the number of session count, as the number of VMs reach more than 4.5 times the number of logical processors, the sessions start to die down. The response time becomes slow, and the results are not consistent. So with 120 logical processor, 480, 485 type VM active session counts should give you a decent result and a consistent performance. Beyond that, the results are inconsistent. So the reason for this narrowing down, if we interpolate this, maybe that the sessions are dying down. That can be the reason. So before moving on, based on login VSI and Bootstorm, it's hard to choose between these two. Results are quite equivalent. Even in case of login VSI, the results for Credit-2 are better than Credit-1. Now coming on to network throughput. It's VM to VM intra-host, 2-socket, 12 cores, 24 logical processor, 20 Debian VM on TX side, 20 Debian VM on RX side with 1 VIF each. And blue one, Credit-1, yellow one or orange one, Credit-2. Credit-2 is lacking behind in network throughput. This is the cumulative result of all the 20 VIFs, all the 20 iPerf threads that are running in all the VMs. So the throughput for the blue line is around 45 gig per second, and for yellow, it's around 42 gig per second, so gap of 3 gig between Credit-1 and Credit-2. Same test, represented in a different way. It's now for each VIF pair. Here, the x-axis represents each VIF pair. There are total 0 to 19 VIF pair here. And this is the throughput. And the dots are for each VIF pair, the performance measurement, the throughput measurements for each VIF pair. And the blue and the yellow line are the mean. Blue is for Credit-1, yellow is for Credit-2. As was seen in the previous slide, Credit-1 scores over Credit-2. But yeah, this is again a different representation of how the throughput for each VF varies. This is again intra-host, same as the previous one, but this is for each VIF pair, each thread. Now the case of inter-host. It's VM to VM, inter-host network throughput, sum of all the threads. Same 8 core, 16 logical processor system, 20 Debian VM on one host, 20 Debian VM on another host, and both the hosts are similar. So we have 20 streams of iPerf running from host 1 to host 2. And the performance, Credit-1 again scores over Credit-2 by a margin of around 3 gigs per second, same as consistent with intra-host. So the results are pretty same. Again, a different representation per VIF. And another thing I forgot to mention, this is for inter-host for jumbo frames. And the size of the jumbo frame that I'm using is 9,000 bytes. So this is the result for that. So this is for jumbo frame. This one is, again, a different representation of a previous graph, VM to VM inter-host network throughput for each thread. It's now for per VIF. Again, 20 VIFs on the x-axis, throughput on the y-axis, and the graph here. Blue one, Credit-1, yellow one, Credit-2. Blue one, Credit-1 scores over Credit-2, as was seen in the previous graph. But again, one important thing you can notice here is the variance and the graph of the blue graph. And these dots for the blue one, they are much more scattered than yellow. I will come to this point again, but this is an important point to consider. There are a lot of ups and downs for this blue one. Yellow one is pretty consistent. The Credit-2 is pretty consistent graph, but for blue one, it's quite varying. This is the point I was trying to make. Now, same test, But now here is the output throughput for each thread. And look at the variance for blue graph, the credit one. And the yellow one is much more centered. It clearly shows that Credit-2 is much more fairer than Credit-1. The scatter is much less for Credit-2. Though the performance for Credit-1 is better, but you can easily see that it's being unfair. The dots over here, they are being deprived. The network throughput is very low. That means CPU is being denied to some of the vCPUs. And here, some are getting extra privileges. So this scatter is quite big for Credit-1. And it's quite concentrated for yellow Credit-2. So at this point, I mean, there is less of a performance difference, but yes, if you have to choose, Credit-2 can be chosen based on, it's much more fairer. And this was one of our design goals, that. Again, the same results. This is not with jumbo frames, normal frames. The performance is almost the same as was seen in the previous results. Credit-1 scores over Credit-2. This is the sum of all threads, same 8-core, 16 logical processors, 20 Debian VMs on one side, 20 Debian on another side, and that's all. Blue one is Credit-1, yellow one is Credit-2. Same for each WIF pair. Again, look at the dots of blue ones, scatter of blue dots. It's quite random, and look at this graph, blue graph. It's quite scattered, it's variable. And same goes, again, the same thing, without jumbo frames also.
So without jumbo frames, it's even more spread out?
Yes, it's even more spread out, yeah. And for Credit-2, it's consistent. There's not much of a difference. Now, the storage performance. This is aggregate disk throughput. Credit-1, blue one, Credit-2, yellow one, 4 socket, 64 core, 64 logical processor, 1 VM, 1 vCPU, and yes, Credit-1 scores over Credit-2. At the bottom is the block size, and at the x-axis is the block size, and y-axis is the aggregate disk throughput. So as the block size increase, yeah, there is a clear distinction between Credit-1 and Credit-2. The performance suffers for Credit-2. This is what 1 VM. Now, this is with 20 VMs per SR. I was surprised. I mean, I checked this around 5 to 6 times how this is happening, but yeah, the performance is pretty much same if we increase the number of VMs. I don't know the reason behind it. We still need to analyze for all the shortcomings in network throughput or the storage throughput, but yes, we need to figure out what's the reason why it's pretty much the same. Yeah.
Turned off. It's on the bottom. Nope. On the side of the bottom there. Little tiny thing.
Got it. Right. So yeah, one question is, what sort of disk, what sort of storage are you talking to here?
It was, I think, tab disk.
No. What physical hardware?
What?
What physical hardware was your storage?
It was not SSD on the systems that I tested. I think it was proper normal SATA disk.
Okay, in which case
Yeah.
that graph is not surprising because you've probably just bottlenecked on the storage then.
Oh, okay. That can be the reason. Yes. Okay. Thanks. And so, yeah, I didn't think about that reason. And just to confirm it, I also got some graph when the block size was 512 byte, and Credit-2 was better than Credit-1 here. Then I increased the block size to 2K. Of course, again, Credit-2 was better than Credit-1. And then the gap started narrowing, and yeah, maybe it has reached the limit. That's why now it has merged. It's pretty same now as we increase the size, now the dots will merge, Credit-2 and Credit-1 performance will merge. There will not be much difference between these two. So again, yes, based on SSD storage throughput, we need to analyze that. Yeah. Now the audio part. I have something to play here. As I mentioned in my first slide, real-time performance audio video was one of the main design consideration while designing this. So whether we have achieved that or not, how can you hear the sound of it? If I play something.
Would this go for the speakers?
It should.
Maybe.
It should.
Where's your?
Yeah. It's a normal bagpipe sound, and when you will hear it, I will play for Credit-1. Just concentrate on the sound, and you will see the difference. And yeah, to explain the scenario, when I tested this, it was one socket, 4-core, 8 logical processor host. I executed 4 VMs, Debian 6 VMs, with 2 vCPU each running kernel compilation, and 1 Windows VM on the host running Windows Media Player, and then I recorded that sound. I think it's not audible. It is? Yeah. Okay. So this is for Credit-1. It's very slow. Yeah, you know. Did you make out the difference? Can you hear it or not? Play again. Yeah, skipping.
How much of that is down to QEMU scheduling in DOM0, though?
Sorry?
I mean, your audio is presumably being emulated by QEMU
Yes.
in DOM0, so it's at the mercy of the Linux scheduler running in the DOM0 vCPUs as well. So how much of it is down to DOM0s?
Passing through an audio card.
Yes, I'm passing.
Oh, this is pass-through,
Yeah.
okay, right.
The GoToMeeting effect.
And now this is for Credit-2. There are no pauses. So yeah, the difference is easily audible and easily observable.
Yeah.
Right. So yeah, that covers it. Questions? So yeah, few things to work on. Myself, Dario, and George will be working on. We will be analyzing. Basic focus will be on network throughput, why it's happening, and yes, of course, storage. I missed that point. I will test with SSD. But yeah, definitely it's much more fairer. And when these tests were done, soft affinity and yield was not implemented. I just want to make that point. So I will rework those, test it, and maybe that can have an impact on heavily loaded system on the performance. So yeah, now we'll be analyzing each of the scenario and then trying to improve.
Does it address one of the problems we saw with Credit-1, I think, which is where it would actively try to steal load from one physical CPU and run it on another if they were idle, so you'd end up with your vCPUs constantly bouncing around the system?
Yeah, so Credit-2 tries to be much more rational about it. So Credit-1 has like no memory. Just at this moment, at different times, things are triggered, and it says, oh, I'm not busy. Who's steal stuff from someone else to run. And so the result is stuff that often ends up just switching around. On the other hand, the CPUs are a lot more evenly utilized. It's really sort of chaotic, but the end tends to be that like the CPUs are often very well utilized. Credit-2 has a much more rational approach, where it's sort of like it keeps track of the historical load, and then it will look for different things and says, okay, well, what would happen if I switch to these? Oh, that's more fair. Let's do that. What would happen if I switch these? Oh, that's worse. What if I switch these? Oh, that's worse. Or if I switch these? Oh, that's better. Okay, we'll do that. But the result, though, is that, so one of the results is that things stay where they are a lot more easily. But the other result is that under certain circumstances, the aggregate throughput can be a bit lower because all the CPUs in the system are not being utilized as efficiently as they could be. So this may be part of the reason why some of the networking stuff is and also, yeah, so does that answer your question?
Yeah, that answers the question. I also wondered if you had any relative numbers on the actual scheduling overhead of Credit-2 versus Credit-1. So, when you take a schedule event, kind of how long is that on Credit-2 versus Credit-1? Because obviously, if it's more complex, it's going to be longer.
Yeah. I don't have any measurements of that yet.
No.
Do you do any like physical CPU topology based decisions like the lowest level cache, NUMA, cluster on die for scheduling vCPUs or helper threads?
So there's a couple of different levels of that. So for Credit-1, so both of them are hyper-thread aware in the sense that they will try to schedule things on different cores before doubling up on two hyper-threads. Does that make sense?
Sure.
There is a thing, so there is a NUMA awareness that's built into the open source version of the sort of upstream version of Zen, so when he said stop affinity is essentially NUMA. So what stop affinity means is, hard affinity means you can only run it on these processors and that's it. Soft affinity says try to run it here first, but if that's too busy, then go ahead and run it somewhere else. Does that make sense? So soft affinity is used to implement NUMA locality, right? So then what you say is, if I have this guest and all the memory from this guest is allocated from the one NUMA node, then I will have a soft affinity toward that NUMA node. And so I'll try to run it there, but if that node is just super busy, then I'll go ahead and run it somewhere else. As far as I know, the Zen server doesn't do anything with NUMA at the moment. Is that right?
Yes.
Okay. And these were all run through Zen server, not through the upstream stuff. These will not have any NUMA locality stuff. Does that answer all the questions you had?
And moreover, when these tests were done, soft affinity was not there even in the upstream version of Credit.
Right.
It was not there.
What about things like cluster on die or like the Xeon Phi kind of topology? So when you place vCPUs on physical CPUs, you can get better performance if your lowest level cache is shared for certain workloads.
Right. So yeah. So as far as cache topology, if two VMs are communicating or sharing a lot of stuff, then you want to have them close together,
right,
cache-wise. If to minimize the number of cache bouncing and stuff like that.
Right.
If two VMs are not communicating and acting independently, then you want to spread them out as far as you can topologically, so
right,
that you can maximize use of the cache. It gets an entire cache to itself. There is no way that for the hypervisor to know which of these two things happens, right? And so at the moment, both of the schedulers assume that there is like basically no communication. And so they always try and spread things out to maximize the cache utilization. Obviously, when that assumption is invalid, then that will cause things to be placed less well.
Yeah, you think that things like the networking performance of VM to VM throughput would improve had you placed them.
Yeah, so if DOM 0, well, the thing is, yeah, if DOM 0 and some other things were placed similarly.
Right.
Yeah, I mean, so there's stuff in place that there's also stuff in place you could imagine, like, if there were several of the network threads placed on, like, a handful of set of pneumatics, such that each guest was talking to a network backend that was local to its own NUMA node, that might have some. So the stuff in place that someone could actually make that happen if they wanted to.
Okay.
It doesn't happen automatically even in the upstream.
All right. Okay. Thanks.
From the performance data, like it seems every time when the test involves the source or destination, for example, the network and one VM is sending the package to another VM. That's kind of the dependency, which is not considered by the scheduling policy, I assume, right?
I didn't get your question.
So if you look at the workloads, the benchmarks,
Yeah.
all of the benchmarks, when the Credit-2 is worse than the Credit-1 scheduling,
Yes.
it has some kind of dependency on the workload. You are sending the package from one VM to another VM. The extreme case is like, suppose you just schedule all of the VMs and are sending package, but they are not receiving the package, then all of them are starved. Then you just store there. And later you schedule the destination VM, you may consume the package, but this probably is worse than like you schedule two VMs that use the same flow and they won't store there. So I'm just wondering, like probably because of the scheduling policy difference between the Credit and Credit-2, like we are trying to balance the workload, somehow it's worse for the workload with the dependency.
Maybe.
It's just
Yeah,
some
yeah,
speculation.
yeah.
I don't know because
Yes.
for the network and the storage stuff, it all seems like they are depending on each other.
Yeah. Possible,
Yeah.
yes. So when we will analyze in more detail, then yes, of course,
Yeah.
we can consider this point. Yep.
One of the things that Credit-1 does is, like I said, it lives in the moment, as it were.
Yeah.
So sometimes what happens is, if I am, I'm sending a packet, and then I send someone an interrupt, and then I go to sleep and wait for that to be handled, right? Well, now this processor is asleep, and there's another vCPU over there that just woke up and isn't running yet. I'm pretty sure and there's a bit of a race whether this processor gets to go to sleep before the other processor actually manages to wake up. But it's quite possible that sort of it sends something off and then says, now what am I going to do? Oh, well, I'll just run that guy. And so that two communicating processes in Credit-1 happen often to end up nearby.
Yeah.
Whereas
Yeah.
in Credit-2, that sort of effect wouldn't happen, won't just sort of happen naturally. But we still need to do a lot more analysis.
Yes.
So these are like hypotheses we haven't.
Yeah, yeah.
Yeah.
Okay.
In networking also, it's not just the two VMs, you've got the threading down there, and there's the bottlenecks on the receiver thread.
Yeah, yeah.
So you've got a three-way schedule.
Yeah, that's also the question. Like, it probably also depends on how you allocate the resource for DOM 0. When DOM 0 is involved, if like DOM 0 happen to be starved, and that will be a bad thing. And especially when the load balancing happens on Credit-2, right? DOM 0 actually becomes a critical domain that should get more resource. And on Credit-1, basically, because it's based on demand, it receives more requests, and then it just happened to get more resource. Right.
Yeah, I forgot. So there's also like a couple of magic hacks in Zen server.
Are you talking about the magic quantum hack?
Yeah. So this problem is sufficient. This problem in Credit-1 is sufficiently bad that there is a patch to the Credit-1 hypervisor in
Okay, so here's another difference between Credit-2 is that in Zen server has a hack to give.
I think it's a cleverly crafted fix.
To give non-zero more CPU time, and that cleverly crafted fix is not ported into Credit-2. So it would actually be interesting to see.
Yes, that's another point. Yes.